Have you ever looked at a tiny speck of dust dancing in a sunbeam and wondered if it was a wave or a particle? It sounds like a question from a sci-fi movie, but it's a real puzzle that stumped the greatest minds of the 20th century. And at the heart of this mystery is a French prince who became a revolutionary physicist, Louis de Broglie. His story isn't just about equations and experiments. It's about daring to ask a question so strange it changed how we see the universe itself. So, who was this man, and how did he come up with an idea that would earn him a Nobel Prize and lay the foundation for quantum mechanics? Louis Victor Pierre Raymond Broglie, or just Louis de Broglie, was born in 1892 into a noble French family. His path seemed set for a life of diplomacy or history, not physics. He initially studied history at the Sorbonne, earning his degree in 1910. But his older brother, Maurice, was an experimental physicist with his own private laboratory. Maurice's passion for the new, exciting world of X-rays and radioactivity was infectious. Louis found himself increasingly drawn to the profound questions these discoveries were raising. The world of physics at that time was in a state of beautiful chaos. Max Planck had suggested that energy comes in discrete packets called quanta, and Albert Einstein had taken this further, proposing that light itself, which everyone knew was a wave, could also behave like a particle, a photon. This idea of duality, that something could be both a wave and a particle, was radical. It was called wave-particle duality, but it seemed to only apply to light. No one thought to apply it to matter. After all, a baseball is a particle. A planet is a particle. You and I are made of particles, and in everyday life, we don't act like waves at all. We don't spread out or bend around corners like. But the First World War interrupted Louis's budding physics career. He served in the army, working on radio communications from a post under the Eiffel Tower. This practical experience with electromagnetic waves likely kept the wave-like nature of the universe at the forefront of his mind. After the war, de Broglie returned to his studies, completely captivated by the puzzle of the atom. Niels Bohr's model of the atom was a major breakthrough, but it had its own strange rules. It said that electrons could only exist in specific fixed orbits around the nucleus, like planets locked into certain paths around the sun. But why? Why only those specific orbits? It felt arbitrary, like a rule without a reason. De Broglie had a flash of genius. What if the electron wasn't just a tiny particle orbiting the nucleus? What if the electron was also a wave? This was the core of his revolutionary idea. He proposed that if an electron is a wave, then for its orbit to be stable, it must exist as a standing wave. Think of a guitar string. When you pluck it, it vibrates in a way that the ends are fixed. It can only vibrate at specific frequencies, creating specific notes or harmonics. It can't just vibrate in any random way. De Broglie imagined the electron's orbit as a circular guitar string. For the wave to fit perfectly around the nucleus without interfering with itself and canceling out, its circumference had to be a whole number of its wavelengths. 1 wavelength, 2 wavelengths, 3, and so on. But not 1.5. This simple, elegant idea perfectly explained why Bohr's electron orbits were quantized. It wasn't an arbitrary rule. It was a natural consequence of the electron behaving like a wave. In 1924, Louis de Broglie presented this idea in his doctoral thesis, titled Researches on the Quantum Theory. The examining committee at the Sorbonne was, to put it mildly, baffled. The idea that a particle like an electron could have a wavelength was unheard of. It seemed too strange to be true. Legend has it they were unsure whether to grant him his PhD or send him to a mental institution. Fortunately, they decided to send a copy of the thesis to Albert Einstein for his opinion. Einstein's response was swift and enthusiastic. He recognized the brilliance and profound implications of de Broglie's work, famously writing that de Broglie had lifted a corner of the Great Veil. With Einstein's endorsement, de Broglie was awarded his doctorate and the world of physics was about to be turned upside down. De Broglie's hypothesis wasn't just a neat explanation. It made a testable prediction. It provided a formula. The wavelength of any object is equal to Planck's as constant divided by its momentum. This is now known as the de Broglie wavelength. For large objects, like a baseball, the momentum is so huge that the resulting wavelength is infinitesimally small, far too small to ever be detected. This is why we don't see everyday objects behaving like waves. But for a tiny, low-mass particle, like an electron, the wavelength should be measurable. It should be comparable to the spacing between atoms in a crystal. This prediction was a direct challenge to experimental physicists. If de Broglie was right, then a beam of electrons, which everyone thought of as a stream of tiny particles, should behave like a wave. It should exhibit wave-like properties, such as diffraction. Diffraction is what happens when a wave passes through a narrow opening or around an obstacle and spreads out. You see this with water waves passing through a gap in a harbor wall, or light waves creating patterns when they pass through a tiny slit. The challenge was to create a slit small enough for an electron wave. The perfect slits turned out to be the atoms in a crystal lattice. In 1927, two separate experiments confirmed de Broglie's hypothesis in spectacular fashion. In the United States, Clinton Davison and Lester Germer at Bell Labs were studying how electrons scattered off a nickel crystal. A lab accident caused the crystal to heat up and reform into larger crystal regions, and when they resumed their experiment, they saw a strange pattern in the scattered electrons. It wasn't random scattering. It was a clear diffraction pattern, exactly what you'd expect if the electrons were waves. At the same time, in Scotland, George Paget Thomson, the son of J.J. Thomson, who discovered the electron as a particle, was firing electrons through a thin metal foil and saw diffraction rings on a photographic plate. The particle his father discovered was, without a doubt, also a wave. The confirmation of matter waves was a bombshell. It validated de Broglie's crazy idea and opened the floodgates for the development of a complete quantum theory. The Austrian physicist Erwin Schrödinger was inspired by de Broglie's work and developed his famous wave equation, which has become one of the fundamental equations of quantum mechanics, describing how these matter waves evolve over time. The concept of wave-particle duality became a central pillar of our understanding of the subatomic world. Everything, not just light, has both wave-like and particle-like properties. Which property you observe depends on how you measure it. It's a mind-bending concept that challenges our everyday intuition, but it's how the universe fundamentally works. For his groundbreaking discovery of the wave nature of electrons, Louis de Broglie was awarded the Nobel Prize in Physics in 1929, just 5 years after his PhD thesis. It was one of the fastest recognitions in the history of the prize, a testament to the immediate and profound impact of his idea. He continued his career in physics, teaching at the Sorbonne and writing many books on quantum mechanics, always seeking a deeper, more intuitive understanding of its strange implications. He was never fully comfortable with the probabilistic nature that the theory later took on, a sentiment he shared with Einstein. He spent much of his later life trying to develop a more deterministic interpretation of quantum phenomena. The legacy of Louis de Broglie is immense and woven into the fabric of modern technology. His discovery is not just an abstract concept for physicists to ponder. The wave nature of electrons is the principle behind the electron microscope. Because the wavelength of an electron can be made much smaller than that of visible light, electron microscopes can be used to see things in far greater detail than any light microscope, allowing us to visualize individual viruses, molecules, and even atoms. Every time you see one of those incredible, highly detailed images of a cell or a material's surface, you're seeing the practical application of de Broglie's theory. His idea that all matter has a wave-like nature is also fundamental to our understanding of solid-state physics, which is the basis for all modern electronics, including the computer or phone you're watching this on. So the next time you think about the building blocks of our universe, Remember the French prince who dared to imagine a world far stranger and more beautiful than anyone had thought possible. Louis de Broglie didn't just solve a puzzle about the atom. He gave us a new language to describe reality itself, a language where particles dance like waves and waves solidify into particles. He showed us that sometimes the most profound truths are found not by following the established path, but by asking a simple, almost childlike question: what if? His intellectual courage reshaped our understanding of everything, proving that even the most solid-seeming matter has a hidden, rhythmic, wave-like heart. Thanks for joining us on this journey into the quantum world. If you enjoyed this glimpse into the life of a scientific pioneer, don't forget to like, subscribe, and hit that notification bell for more stories from the history of science. Let us know in the comments which scientist you'd like to hear about next. See you in the next video.